Hi, everyone. So for population data, how could we calculate a population variance or population standard deviation, or SD? And we're going to go through this, even though we're not going to repeat these calculations all throughout the semester. That'll be quite tedious. But we should go over the ideas behind how to compute these and go through the process. Now, as we compute these, we're also going to need to find the population mean at some point, mu. And since we have population data, census data at hand, we won't have to deal with samples. We don't need this stuff. Okay. All right, at least not for now. So what's the idea behind population variance and standard deviation? All right. Now, the idea is we're going to focus on the population mean mu as a reference point. So we have a flag planted at the mean mu, right? And we want to measure the spread of the data values around the mean. So assuming that we have the same scale on these two axes, the mean here, planted at the same number, what data set would exhibit higher variation or spread? Well, probably the data set down here. They're more spread out about the mean. Like over here. Now it's true that they have the same range. The two data sets here have the same range. Max minus min is the same. And yet we have the sense that this data set here is going to be more spread out than this data set. They're more spread out about the mean. Well, let's see why. It does turn out that the second data set would have a higher variance or standard deviation. All right. So here are the steps. It's a recipe. Given capital N data values, x sub 1 through x sub n, step 1 is to find the population mean, mu. So I'm going to write out the steps in the left column. The notation will be in the right column. This is our classic formula for population mean. You take the sum of the data values, divide by the population size. And then you find the deviations from the mean by subtracting the mean from all the data values. All right. So we're going to recenter the data so that instead of mu, the new data set will be centered at 0. That's a way of standardizing things. We're going to subtract off the population mean from all the data values. All right. We're going to square these deviations. Below a column for these values. The variance will be the average of these squared deviations. We take the sum of these values from step 3. We take these values, take the sum, add them up, divide by n. The standard deviation is always the square root of the variance. So ultimately, it comes down to this formula for population standard deviation. Obviously, an example will help. Let's look at an example. All right, let's go back to the 5 test scores from before. I have them in this column, and they don't have to be sorted. So let's say we have the 5 test scores for all 5 students in the class. This is census data. We have all the population data we want. The first step is to work out the population mean, mu. We get that from adding these up and then dividing by 5. We get exactly 87.8 points. In any case, we want to round off to 1 decimal place anyway. So that's step 1, finding the population mean. And then what do? We find the deviations of these scores from the mean by subtracting off the mean. So 80 minus 87.8, we're subtracting off the 87.8 here. That's negative 7.8 points. The fact that this is negative indicates the fact that the 80 points was below the mean. It was 7.8 points below the mean. And so forth. We subtract off the mean. This was way below the mean. This was above the mean. That's a positive deviation. Below the mean, above the mean. All right. So these are the deviations from the mean in this column. Now a student might ask, so as a measure of spread, why don't I just take the sum or the difference of these deviations? Well, try this out on your calculator. What is the sum of these deviations? And for that matter, what's the average of these deviations? it turns out that the sum and the average of these will be a big ol' 0. How's that for a measure of spread? I don't think so. We have some different scores here. We'd only get 0 variance, variation, or standard deviation if these are all the same score. So it would be inappropriate to take the sum or the average. It would just be 0. The sum would be 0, the average would be 0. That doesn't tell me anything about spread. So what can we do to these deviations to make sure that the results here will be non-negative? Now, one response might be absolute value, and that is a possibility. That would lead to what we call the mean absolute deviation, or the MAD, the MAD. But it turns out that statistical theory doesn't like that as much. So what else can we do to these values to make sure that these results are non-negative? Well, we can square these values. And the square of positive and negative values will all be positive. So the square of negative 7.8 is positive 60.84, and so forth. We square these deviations. Now in practice, we would normally fill out the table row by row. So once we calculate the mean, take the 80 points, subtract off the mean, we get the deviation, negative 7.8 points. And while that's still in your calculator, you would square that, and the result will be 60.84. You know that these square deviations cannot be negative. All right. Likewise, you take the 76, find the deviation from the mean, square that result while it's in your calculator, and you get this big number, and so forth. So as you fill out these tables, you should fill them out row by row to save time. You don't have to keep re-entering these numbers. All right. So now we have these squared deviations. And by the way, statistical theory likes what we're doing. It likes variance and standard deviation. Now, what do we do with these squared deviations? These are the things that we're going to average to get our population variance. How do we take the average? We take the sum and divide by 5, capital N, the number of values. All right, the sum is 520.8. We divide by 5, and we get the population variance. The variance, population variance, sigma squared, is the average of the squared deviations, the sum of column 3, the sum of these values, divided by 5. We get 104.16, and it's a weird unit. It's in square points. What's a square point? Good question. That's one thing we don't like about variance, the fact that the unit often doesn't make sense. And by the way, we could round this off to 104.2 square points, but we're going to use this to find the standard deviation, the population standard deviation. So I'll keep this exact for now. This is exact. All right. So the population variation will in fact be exactly 104.16 square points. Now, one reason why we prefer the population standard deviation, the SD, over the population variance is that the units for standard deviation are natural. They're going to be in points, like for the original data values. So step 5, the standard deviation, sigma, is the square root of the variance. The square root of 104.16 is about 10.2 points. We round off to 1 decimal place because the original data values were in integers to 0 decimal places. The population standard deviation of the data is about 10.2 points. And it shares the same units as the original data values, good old points, which makes total sense. Now on your scientific calculators, you should have a sigma or sigma sub capital N button that will allow you to work out population standard deviation. If for some reason you need the variance, you could do what to these values? You could square them. Because remember, standard deviation is always the square root of the variance. I'll do this in blue. Standard deviation is always the square root of the variance. The variance is always the square of the standard deviation, whatever the context. All right. And how would you do this on Excel? All right, so let's say that we have 5 test scores for the 5 test students. For the population standard deviation, it's equals, you need that for commands, STDEV for standard deviation, dot P, that's for the population standard deviation. This is full census data. It's a population data set. Parenthesis, I can sweep over the entries. It's A2 to A6. End the parenthesis. And we get, lo and behold, it's about 10.2 points. It verifies what we got over here. For the population variance, you can just square that or directly equals, it's var.p for population variance. For these data points, 104.16 square points. Okay, next up, how do we work out sample variance and sample standard deviation? How is that a bit different? Next time.